So here we are trying to evaluate limits, and there are some techniques to evaluate limits. You can either use a graph, or you can use a table, or you could do basic algebra to get to the limits. So here is a graph, and the function doesn't have any breaks. That is the first thing to notice. So if the function doesn't have any breaks, we call it a continuous function. And for continuous functions, the limits are the value of the function at any point. So here we have 2 points, 1 and 3. I do not see a discontinuity there. I do not see a discontinuity there. So no discontinuities. So since there are no discontinuities, it would simply be the value of the function. So limit x approaches 1, f of x, would equal to minus 2, which is the value of the function at x is equal to 1. And likewise, limit x approaches 3, f of x would simply be equal to 0, and that would be the value of the function there. So we get 0. In the next graph here, there is a discontinuity. So that open dot indicates a discontinuity. And that is not a discontinuity. And as a whole, is this a function? It is a function, but it is not a continuous function. All it takes is one discontinuity to make the function not continuous. So since at 2 we do not have, at negative 2 we do not have a discontinuity, so it would simply equal to the value of the function. But at 0 though, there is a discontinuity. So let's approach it from the left-hand side and the right-hand side. This is not a jump discontinuity. So and that would mean the right and left limits will be the same, and the limit will exist. So limit x approaches 0 when you approach it from the right-hand side it is getting closer and closer to 0, minus 3, and limit x approaches 0 minus from the left-hand side, it is approaching minus 3. So they are the same. So limit x approaches 0, h of x would simply be equal to minus 3. So this is a tabular method. So anytime you have a tabular method, we need to have a calculator. So going to use my calculator here. I'll show you how we can use the calculator to evaluate all of this with a few easy steps instead of plugging in the value of x each and every time. So the function that we have is 2x plus 3 over 5. So the first step is to go to the calculator and type in 2x plus 3 divided by 5. Then you exit by pressing second mode and press second window. It says table set, which means table setup. So here the value is 5.9. So we will start at 5.9 and we can increment it, but since they are not equal increments, I'm simply going to say ask, which means it is going to ask us each time what value to plug in. Second mode to exit, and second graph would give you a table. So I am going to enter 5.9, the first value. I get 2.96, 5.99, I get 2.996, 5.999, I get 2.9996. So it seems like the function is approaching three from the left-hand side. From the right-hand side, if I plug in 6.1, I get 3.04, 6.01, I get 3.004, 6.001, I get 3.0004. Again, from the right-hand side, the function seems to approach 3. So naturally, the limit as x approaches 6, f of x would simply be 3. Now, this is a function that is continuous. I know it, but if you can't recognize it, you can simply graph. So if you hit graph, you get that function and you see no discontinuities. So I could have simply plugged in the value of the function. So f of 6. What is f of 6? F of 6 is 2 times 6 plus 3 divided by 5, which is 15 over 5. You get 3. And that goes with the remark that I wrote earlier, that if the function doesn't have any discontinuities. It is a continuous function, and for a continuous function, the limits are simply the value of the function at any point. It is always good practice to try and simplify the function prior to evaluating a limit. So in this problem, we have f of x equal to x minus 4 divided by x squared minus 5x plus 4, which I could write it as x minus 4 divided by x minus 1 times x minus 4. I'm simply factoring. So those two would go away, and this would result in 1 over x minus 1. Now, if I graph this, there is a discontinuity, but that discontinuity is at 1. But there is no discontinuity at x is equal to 4. So since there is no discontinuity at x is equal to 4, this would mean the limit x approaches 4, f of x would simply equal to f of 4. I plug in the function, I have 1 divided by 4 minus 1. It's 1/3. It's 0.3333. Let's see if we get the same value with the table. So I'm going to approach 4 from the left-hand side. So 3.9 gives us 0.3448. 3.99 gives us 0.3345. 3.9999, well, you could keep on doing it, but you have 0.3334. And from the right, so it does look like it is approaching 0.333 from the left-hand side. From the right-hand side, when I plug in 4.1, I get 0.3226, 4.01, 0.3322, 4.001, you get 0.3332. Now we can only get closer to the limit value, we won't get the exact value because the exact value could only occur at x is equal to 4. So that is 0.333, and we know the limit is in fact 0.3333. So the value of the function is 0.3333, but according to what we know, we could simply say the limit as x approaches 4, f of x is 0.333. You know, in decimal values, with 3 digits, that's all we could match with the limit. Now, you may ask me, well, we could have simply plugged in 4 in the function. If you plug in 4 in the function, we will get an error because in the denominator we had x minus 4. So when you plug in 4, you have 4 minus 4, and you get a 0, and if you have a 0 in the denominator, it is undefined. So we can't do that. So there is a way to tackle radicals, which we will talk about later. But we'll just use a table to first find the limit. So square root of x plus 2 minus square root of 2 divided by x So I'm going to approach it from the left-hand side. Approaching 0 from the left-hand side. So f of x is simply square root of x plus 2 minus square root of 2 over x. Negative 0.1 gives me 0.3581. Negative 0.001 gives me 0.3536. Negative 0.001 gives me 0.3536. And it looks like the limit is 0.3536 at 0. From the right-hand side, when I plug in 0.1, I get 0.3492. 0.01, I get 0.3531. 0.001, I get 0.3535. So 0.3536, I could round it and write it as 0.354. I could do the same thing on the other side and round 0.3535 to 0.354, which would imply the limit x approaches 0, f of x is equal to 0.354. And we could have looked at only the first 3 decimal values and given the answer as 0.353. Keep in mind, you can't match every single decimal when you're evaluating left and right limits, decimal digits, I mean. We can only come closer to about 3 decimals or 4 decimals like we have seen in the past 2 problems. So first up here we have a function f of x. F of x is 1 minus x squared. We want to know if it is continuous. Let's see if it is continuous. So 1 minus x squared, I know it is continuous. So if you graph it, no issues whatsoever. It is a continuous function, and it is continuous at 1 right there. So it would simply be equal to the value of the function. So we have 1 minus 1 squared, we get 0. Here is another function, and the first thing that we would do is to see if it is a continuous function. 2 divided by x plus 2 graph, and f of x is not continuous. There is a break at x is equal to -2, which we can see up there. Let's see if I can grab a picture. Wouldn't let me. Okay. So you can just look at the picture over here and you can see that at x is equal to -2, wonder if I could paste it over here. Okay, let's not deal with that. At x is equal to -2, there is a break. But if you look at less than -2, f of x is continuous. It's just a line that is going down toward -infinity. So limit x approaches -3, 2 over x plus 2 would simply be equal to f of -3. So we have 2 over -3 plus 2, which is 2 over -1. The answer is -2. So here we have x squared minus 1 divided by 2x, and I know that this is a continuous function. It's always great to use parentheses when we have rational functions such as this one. Graph, whoops, where did I go wrong? Parentheses. So it seems like the function is not continuous. And it has a break or discontinuity at x is equal to 0. But for x less than or equal to 0, f of x is continuous. So the limits only matter at points of discontinuity. And -2 is not a point of discontinuity. So limit x approaches -2, x squared minus 1 over 2x would simply be equal to f of -2, which is -2 squared minus 1 divided by 2 times -2. So 4 minus 1 over -4, you get 3 over -4, which is minus 3 over 4. So here, f of x is 2x squared minus x minus 3. And we divide that by x plus 1. We want to evaluate the limit as x approaches negative 1. So the first question to ask is x equals negative 1 a point of discontinuity? So plug in at negative 1 for x. We have 2 times negative 1 squared minus negative 1 minus 3 divided by negative 1 plus 1. So you have 2 times 1 plus 1 minus 3 divided by 0. 3 minus 3 over 0, you get 0 over 0. Now, 0 over 0 is not undefined, rather it is an indeterminate form. So graphing this, and it doesn't seem like the function has a break, but let's narrow the window a bit more, or zoom in. I'm going to put 30, 30. And at negative 1, there is a discontinuity. So let's say if we can evaluate that particular limit. So what value does it approach at x is equal to negative 1? First thing to do is there a way to simplify the expression? That's the first thing that one should think of prior to evaluating a limit. So in the numerator, we have 2x squared minus x minus 3. And could we factor that? I think we should be able to. 2x squared plus 6x minus 5x or minus 6x, that wouldn't work. So the product of the first and the last term would be negative 6, and we'd like to get a negative 6. So perhaps negative 3x minus 2x would work, or plus 2x. So if I pull x out, we have 2x minus 3, and 1 out, we have 2x minus 3. We have 2x minus 3 in common. So if I pull that out, we have x plus 1. So I could rewrite the function like so, and those two would go away, and limit x approaches negative 1 to x plus 3. Now, if you look at it, the 2x plus 3 part is a straight line. It is a continuous function. So we just have to plug in the value. So 2 times negative 1 plus 3, 3 minus 2, you get negative 1. So, oh, bad math. Positive 1. So that would be the limit of the function. So here is a strange looking function where we have x cubed plus 27 divided by x plus 3. And clearly f of x is x cubed plus 27 divided by x plus 3. And f of minus 3 would be x cubed plus 27. We can plug that in. Minus 3 plus 3. Clearly we end up getting negative 27 plus 27 divided by 0. We're ending up in the same issue that we had previously. So first question to ask is, could we simplify the function? By the looks of it, you may say, oh no, we cannot simplify this. But by all means, we can. If you remember the identity, a cubed plus b cubed is simply a plus b times a squared minus ab plus b squared. Likewise, a cubed minus b cubed is a minus b times a squared plus ab plus b squared. These are identities from algebra. So in the problem, a is x, b is 27. 27 is simply 3 cubed. So this would mean x cubed plus 3 cubed would equal x plus 3 times x squared minus x times 3 plus 3 squared. So you have x plus 3 times x squared minus 3x plus 9. So I'm going to rewrite the function limit x approaches 3, x cubed plus 27 over x plus 3 would equal to limit, I meant to write negative 3. Those two would go away, and you have limit x approaches negative 3, x squared minus 3x plus 9. Now, when we plug in the negative 3 in there, I can directly plug in negative 3 because x squared minus 3x plus 9 is a continuous function. It is a parabola for all values. So since that is continuous, I could simply plug in the value negative 3 squared, negative 3 times 3 plus 9, which would give me 9 minus 9 plus 9. Those two would go away. Oh, sorry, it's minus 3. Minus 3 squared minus 3 times negative 3 plus 9, which would give me 9 plus 9 plus 9 is 27. So I always said, try to come up with a way to simplify so that we could evaluate the limit. Here, f of x is square root of x plus 1 minus 2 over x minus 3. If I plug in 3, clearly there would be a discontinuity. So as I've shown earlier, you can make use of a calculator to identify the discontinuity as well. So square root of 4 is 2, 2 minus 2 divided by 0, the same issue that we had before. 0 over 0 is not a proper value. It's called an indeterminate form. So how do we go about doing this? I said, oh, simplify f of x, but we cannot do it because there is a radical. So if you go back to algebra, we can multiply and divide by the conjugate of the radical. So you can see if we have x plus 1 minus 2, this, or square root of x plus 1 minus 2, its conjugate would be square root of x plus 1 plus 2, and vice versa. So the numerator, I will have square root of x plus 1 squared plus 2 square root of x plus 1 minus 2 square root of x plus 1 minus 4 divided by x minus 3 times square root of x plus 1 plus 2, which would give us x plus 1, these two would go away, minus 4 over x minus 3 times square root of x plus 1 plus 2, which is simply x minus 3 over x minus 3 times square root of x plus 1 plus 2. So the answer would be 1 over square root of x plus 1 plus 2. So whether I take the limit of the original function or the limit of the reduced function, which we have here, they are one and the same. So the reduced function, though, it is continuous. So when I plug in 3, the denominator is not going to become 0. So we have 1 over square root of 3 plus 1 plus 2. So 1 over square root of 4 plus 2. We have 1 over 2 plus 2. So the answer is 1 over 4. So the limit of the original function is 1 over 4. So the last one is a piecewise defined function. We have seen this before, but I'm going to show you how to do this without using a graph. So clearly the breakpoint is 4. So we divide the pieces at x is equal to positive 4. So the breakpoint is at 4. So since we have a less than or equal to on one side and greater than on the other side, in the first piece, since we have a less than or equal to, we can plug in s equals 4. And that would give us f of 4, which is 3 times 4 minus 4, 12 minus 4, we get 8. But in the second piece, though, when we plug in 4, even though we cannot do that. So hypothetically, suppose x is equal to 4, or s is equal to 4. In the second piece, f of 4 would be 5 minus 1/2 times 4. We get 5 minus 2, which is 3. So clearly, on one side it is 8, on the other side it is 3. If you can't see it, at 4, the first piece gives me the value 8. And since it is less than or equal to 4, close dot, in the second piece, at 4, we end up getting 8. 3. And clearly, what we observe is a jump discontinuity. And as I mentioned earlier, anytime we have a jump discontinuity, I don't know if I mentioned it earlier. I didn't. I'll put it as a remark. Anytime we have a jump discontinuity, a limit will not exist. Why so? When I approach, I could draw this. If you look at the two pieces, 3s minus 4 is mx plus b, so it is a line, so it's going like that. 5 minus 1/2 s over 2 is also, if I rewrite that, that would be minus 1/2 s plus 5, mx plus b. That is also a line, but with a decreasing slope, so it's going to go, do I have it backwards? Yes, I have it backwards, I'm sorry. So for x greater than 4, it is a decreasing line. And for x less than or equal to 4, it is an increasing line. And clearly there is a break. So as I approach 4 from the left-hand side, I would end up getting 8, so getting closer to 4. On the x-axis, the y value is approaching to 8. Likewise, limit s approaches 4 from the right-hand side would equal to 3. The limits don't match. This would imply limit s approaches 4, f of s, I meant to write s, it's a habitual thing, is simply dne. The limit does not exist. So things to know: if we have a point discontinuity, limit will exist. If we have a jump discontinuity, the limit will not exist. If we have an infinite discontinuity, the limit will not exist. And prior to evaluating a limit, always try to simplify. If you simplify, you may not even need a graph or any other technique to evaluate the limit.